mess. Alrighty, good morning lads and ladies. Welcome back to MAC2312, that is Calc 2 on this lovely 17th of September. Excuse me while I get my shit together. It's just one of those mornings. Today is designated as a lab day, so I think it's appropriate, especially given where we are in the course, to spend some time just solving problems, because I know over the last couple weeks I've dumped a lot on you. So we're going to solve some problems today. We're going to solve a mixture of problems today. I'm going to let you guys have a say in what some of that problem solving is. So right now, while things are starting to get together, if you could take a look at your notes, homework, whatever, and see what problems you would like to work. If you have the problem itself written down, that's wonderful. I'll also get the last few homework sets up in WebAssign, so if you just know you want homework 3, problem 5, or whatever, you can say that. And once you know you'd like to see a problem, type it in the chat. And then I will solve those problems in the order they come in. The other thing I'd like to do today is to give you a more tractable feel for where we're going in section 7.4. So you do have some 7.4 homework problems in the current homework set, homework 4. Those are going to be due on Monday for you guys. So I just want to I'm going to show you a little bit how that works, and then we can dive into solving homework problems. I'm going to go ahead and turn on the document camera, flip on the screen share, and we can start doing the thing. Oh. Connect. Yeah. Alright, like we said, this is MAC2312, section number 004, Calc 2, and the date is the 17th of September. Alright, so like I said in class last time, we are actually approaching our first test. Once we finish section 7.4, that's the last bit of like new content that you guys need to learn before the test. There is one textbook session after 7.4 that is technically included on exam 1. Yeah, I fed the puppy. That's section 7.5, but that doesn't actually contain any new material. 7.5 is a strategic thinking section where they talk about how to integrate different functions. Like, do you start with by parts? Should you do trig sub? You know, which of these methods ought you apply to a given problem? So I can show you that really quickly here. First, 7.5 has an expanded version of this table of integrals that you should know. Definitely, all of these are things you should know well. For example, down here you see this one that we proved yesterday or last time. It's a little bit more thorough than the table in 5.4. Right, these last few rows are new. Alright, but you see the rest of it is just like, okay, what things should you try in what order? So like simplify, look for an obvious substitution, and then, you know, decide whether you're looking at a trig integral or something you should do partial fractions with, or something you should do integration by parts with, and so on. So that's where we're going, and that's the last section we're going to talk about before the test. It serves as a really good review section for the test, but this is what we need to button up. So, let's talk a little bit about partial fractions. Partial fractions is an algebra process for splitting proper rational functions up into simpler pieces. And you'll notice there's nothing about integration or differentiation or any calculus here. Partial fractions is not a calculus thing, it's an algebra thing. But it's an algebra thing that can sometimes make calculus things easier, right? We know how to integrate very simple rational functions like 1 over x. 1 over x is a rational function, and I know how to integrate that. But if you give me more complicated rational functions like 1 over x times x plus 1 times x minus 3, all of that downstairs, I don't right away at least know how to integrate that. But if I could split that function up into something to do with 1 over x plus something to do with 1 over x minus 1 plus something to do with 1 over x plus 3, then I could handle that. The simpler pieces come from the factors of the denominator. And the procedure varies a little bit depending on what the factors of the denominator look like. So I'm going to run you through some basic theorems from algebra, and we'll see how the partial fraction decomposition is affected by the different possible factors of the denominator. First, definitions. What's a rational function? Let's make sure we all know what we're talking about. Who can help me here? What is a rational function? What color is the sky? Does poop smell good? Is anybody here? Come on, guys. I know it's Friday. Alright, thank you for the thumbs up. I appreciate that. So the sky is blue, poop smells bad. Can anybody tell me what a rational function is? Yeah, my wife just shouted from the back. A rational function is an expression of the form, I'll call it r of x. This is the notation we use in pre-calculus. R of x is equal to p of x over q of x. Right, it's a fraction. It's a function that is a fraction. But there are some special conditions on the objects p and q. They have to be polynomials. So no square roots or anything like that, right? No square roots of x. So a rational function is a ratio of two polynomials, right? I trust everybody remembers what a polynomial is. It's a linear combination of positive integer powers of x, non-negative integer powers of x. Partial fractions is something we can only do with rational functions. So if the function you're trying to integrate isn't a rational function, then there's no sense in even thinking about partial fractions. In addition to that, it's something we can only do for proper rational functions. So a rational function is called proper if the degree of the top, so I'll call this degree p, is strictly less than the degree of the bottom. Right. So if the top is a degree 3 polynomial having x cubed as its largest power, then in order to be a proper rational function, the bottom would have to be at least a degree 4 polynomial having x to the 4 or larger show up somewhere. I can only do partial fractions to proper rational functions, and the first little roadblock most people hit when they come into this section is forgetting how to take an improper rational function and rewrite it in terms of a proper one. The catch is long division. You need to long divide. Been in class for a few minutes and I haven't written anything to do with calculus down. Let's try this. The integral here is an integral of a rational function. Right? The thing inside is a ratio of two polynomials. The top is just x cubed, that is a polynomial. The bottom is x squared plus 1, that is a polynomial. The degree of the top is 3, the degree of the bottom is 2. So this is not a proper rational function. Let me do solutions in a different color. X cubed over x squared plus 1 is not a proper rational function. So the thing we need to do is to long divide. I need to divide this by this and rewrite it as some polynomial plus some proper rational function. So we'll use polynomial long division to clean this up. Here's how you divide x cubed by x squared plus 1. You write your x squared plus 1 over here. You write your x cubed here. You could write x cubed plus 0x squared plus 0x plus 0 if you want. X squared goes into x cubed x times. Right? X times x squared is x cubed. If I multiply x by x squared plus 1, I get x cubed plus x. And if I then subtract that polynomial from the one above, the x cubes will go away, and I'll have a minus x. Since this cannot be divided by x squared, we're only paying attention to the lead term here. I don't give a fuck about the 1 in each of these steps. Since there is no polynomial I can multiply x squared by to turn it into x, I'm actually done at this stage. So this piece down here is called the remainder. Just like when you learned how to do division with integers in 2nd grade, this piece up here is called the quotient. And what this polynomial division shows us is that x cubed over x squared plus 1 can be rewritten as x, this quotient, plus negative x over x squared plus 1. So you take the quotient, that's the output, and if the one thing neatly divides the other, then you'll just have the quotient. The remainder will be 0. But if you have a non-zero remainder, you take that remainder and you put it over the divisor, the thing you're trying to divide by. Alright? Now this I know how to integrate, and this I know how to integrate, so we can reapproach the problem. I can now say, therefore, the integral of x cubed over x squared plus 1 dx is the same as the integral of x, alright, this is minus x over x squared plus 1, because that's how everybody would write it, dx. Alright, if this is equal to this, then the integral of this is equal to the integral of that. Now we'll split up the integral. This is the integral of x dx minus the integral of x over x squared plus 1 dx. And we're going to split that up because they take different techniques. The integral of x dx is not anything special. How do I do this integral?
You sub.
Sub for what?
X squared plus 1.
Very good. We're going to sub for the bottom. I'll use the letter z. It's because I have an allergy to the letter u. If z is x squared plus 1, then dz is 2x dx, which is the same as saying 1/2 dz is equal to x dx. The first integral doesn't get that substitution, only the second one does. So the first integral I know it's 1/2 x squared. And then I'll have minus 1/2 integral 1 over z dz. The x times dx is 1/2 dz, so that's where the 1/2 is coming from. And then I'm left with 1 over x squared plus 1, that's 1 over z. So this integral is 1/2 x squared minus 1/2 times the natural log of the absolute value of z plus a constant. And the natural log of z is the natural log of x squared plus 1. I can actually ditch the absolute values because x squared plus 1 is always positive. But if you left them, that would be fine also. Okay? So you will run into problems where you have to integrate a rational function which is not proper. And you should think of those as like bait. Those problems are trying to catch you out. They're trying to see if you'll do something silly and like try to run partial fractions and waste your time on this. But you shouldn't. If the degree of the top is not strictly less than the degree of the bottom, so even if this was an x squared, you do long division and then reapproach the problem. Otherwise, you spin your wheels with partial fractions. You won't actually get anywhere. Okay, so we don't always do partial fractions, but when we do partial fractions, how do we do it? If you're going to run partial fractions, you need to begin with a setup. This is where you assume that your function can be written as a sum of simpler functions of the form whatever. The way it works is that each factor of the denominator contributes a term to the partial fraction setup, or maybe multiple terms. Just like you have a trig sub Bible, there's a PFD setup Bible kind of thing. It goes like this. So the denominator contains a factor of the sort I'll put here. Then your PFD setup must contain the thing I put over here. If your denominator just has a simple, non-repeated linear factor, something like x minus c, then your PFD setup will contain a term like a over x minus c. If your PFD setup, or if your denominator has a repeated factor, so a linear factor, but instead of just being x minus c, a regular linear factor, it's repeated some number of times, has some multiplicity m, which is not 1, then your PFD setup will contain a number of terms. You have to build up to that multiplicity. I suppose I should make clear this is like a capital C, different from the lowercase c that I'm using for the root downstairs. So if you have like x minus 1 cubed, your PFD setup would have a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed, all just from that one term. These aren't so bad. Things can get worse though. If you have something like, and there's unfortunately no nice way to write this, if you have an irreducible quadratic factor, that is a quadratic expression in the denominator, a factor, that cannot itself be factored further, right? That does not have real roots, then your PFD setup has to contain a term with a linear numerator. And then the nightmare case is if you have repeated ones of these. Now your homework, the homework that's due on Monday, only has the nicest possible cases, but you will have more homework coming out that will contain stuff like this, and even this nasty third case, or fourth case. So an irreducible quadratic factor raised to some multiplicity. This could be like x squared plus 1 all cubed. In this case, you'll have something like this. And you have to build up to that multiplicity with a bunch of terms that each look like the thing from the irreducible quadratic. Like this. Alright, this is your partial fractions setup guide. And I'm going to give you a lot of little bits of information to help. Like I'm going to tell you how to tell if a quadratic is irreducible quickly. I'm going to show you a trick for finding the coefficients a, b, c, d in these nicer cases without going through the whole process. I'm going to try to convince you that the mechanism we use to find those coefficients is valid, and then we're going to practice a little bit. I'm going to hold here for a second in case anybody needs to write. Please do put this somewhere neatly in your notes. You can refer back to it because you will need to do that. Are there any questions about what it is this thing is communicating? Okay then, as in our example from Wednesday's class, once you set up your partial fraction decomposition, once you've written your function as a sum of things that look like these, you need to find the coefficients or the constants a, b, c, d, whatever. I'm going to do a brief kind of aside to explain how that works, because most people have takes a second. So the question is, how do we find the constants so on from the PFD. So PFD, again, stands for partial fraction decomposition. It just takes too much time to write. The answer is going to come in the form of another question. If I tell you that negative 2x cubed plus 3x squared plus 5x minus 1 is equal to a x cubed plus b x squared plus cx plus d, what are a, b, c, and d? And I really want an answer here, so who can help me with this? Anybody tell me what a would have to be?
Negative 2.
Damn
X.
right. Yeah, right? The coefficient of x cubed on the left is negative 2. The coefficient of x cubed on the right is a. So a would have to be negative 2. I'm sorry, I interrupted you. What would the letter b be?
3.
Yeah. You guys see what we're doing here? We're just matching the coefficients. C, the coefficient of x on the right, would
5.
be 5. D, the constant term on the right, would have to be negative 1. That's it. And this is what we do when we solve partial fractions problems, when we go to look for those coefficients. The difference is that your PFD setup doesn't look like this right away. It doesn't look like two polynomials being set equal to one another. It looks like some rational function being set equal to some sum of simpler rational functions. So in order to get into a position where you can do the thing like this, equating coefficients, you have to take your PFD setup and rearrange it algebraically to look like an equality between two polynomials. Does anybody know why we can do this? Why are the only numbers that could work for a, b, c, and d negative 2, 3, 5, and negative 1? This is a question that's just barely beyond the scope of this class, but I'm curious if anybody has encountered the term before.
Because of the power of the x.
Yeah, it's deeply connected to the power of x, right? I'm able to set the coefficient of one power of x equal to the coefficient of the other power of x. The reason for that this is a word for you to Google. Due to the linear independence of 1x, x squared, x cubed, x to the 4, and so on, this set of integer-powered power functions forms what's called a linearly independent set. This is a term from linear algebra. This is like matrices, vectors. This terminology comes from that field of mathematics. It turns out polynomials are vectors. Nobody told you that shit, did they? Polynomials are fucking vectors. They're vectors in the vector space of all polynomials. They're not like arrows like vectors you see in physics, but they're still vectors. It turns out a vector can be anything. My chair can be a vector, this coffee cup can be a vector. You, my friend, are a vector in the appropriate vector space. A vector is just an element of a vector space. Polynomials of a given degree form a vector space, and the set of non-negative integer-powered power functions form a linearly independent spanning set for that vector space, which has another name. It's called a basis. And this is a special basis. It's an orthonormal basis, which means the only way these sort of things can be equal to each other is if this term is equal to this term. You can ignore all the other shit. This term is equal to this term. You can ignore all the other shit. This term is equal to this term. You can ignore all the other shit. If that sounds fascinating to you, I strongly encourage you just Google the word linear independence. You'll find lots and lots of good stuff which will help you later in your mathematics career when you take MAS 4105 or MAS 3200 whatever, the bullshit computational linear algebra class, if you elect to take that one when you get to university. It's a deep thing, and it's a beautiful thing, and it's what makes partial fractions work. So let's do it. Grab a problem from your book to ensure things don't get out of hand, because they easily can. What's a not so bad one? Yeah, we'll look at just setting up a PFD thing. Okay, I'm going to write this with the factored denominator already. Now we need the practice factoring, right? Okay, let's do the whole thing. Evaluate integral x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x. Oh, that's easy to factor. Okay, I thought we were going to have to do something fancy. All right. So, I have here an integral of a rational function. The rational function is proper because the degree of the numerator is 2, the degree of the denominator is 3. So the degree of the top is strictly less than the degree of the bottom. That means no long division. We got to proceed with the partial fractions. In order to proceed with the partial fractions, I need my PFD setup. In order to get my PFD setup, I need to know the factors of the denominator. So first, factor the denominator. Two x cubed plus 3x squared minus 2x. Every term there has an x in it, which can come out, and then we're left with 2x squared plus 3x minus 2, which is a quadratic that we can factor further. I don't know if you guys remember the trick to factoring these sort of things. It's usually called the AC method. So a times c here is -4. I need two terms who multiply to -4 and sum to +3. That would be +4 and -1. So I rewrite this as 2x squared plus 4x minus 1x minus 2. And then factor by grouping. I can pull out a 2x from the first two terms, and I'll be left with x plus 2. I can pull out a -1 from the second term, and be left with x plus 2. So this is x times 2x minus 1 times x plus 2. Okay, so that's the factored denominator. Which means this function can be rewritten my function is x squared plus 2x minus 1 divided by x times 2x minus 1 times x plus 2. And now we're going to set up the partial fractions. Each factor of the denominator is a linear factor. This one doesn't look like x minus c for any value of c, but if you force factor out the 2, then this would be x minus 1/2. It's a simple linear factor. X is the same as x minus 0. All right, so each one of these is a simple linear factor. So each one's going to get a single term. Here's the term that comes from the factor of x. Here's the term that comes from the factor of 2x minus 1. Here's the term that comes from the factor of x plus 2. This line right here is called the PFD setup. You will have problems in your homework and problems on the test that say, just give me the PFD setup. Don't evaluate the integral, don't do any partial fractions work beyond that. Just give me the PFD setup. This is what I want. WebAssign just wants this, right? When they ask you for the setup, they just want this. Now, we need to go from this expression to something that looks like this. And the only way to do that is to clear out all the denominators, right? The reason this doesn't look like an equation between two polynomials is because there's all this shit downstairs. And thankfully, it's the same shit on both sides. So that's by design, right? Same denominator over here as what you would have with a common denominator over here, if you put them together. So if you want to turn this into a polynomial expression, you need to multiply both sides by x. You also need to multiply both sides by 2x minus 1. You also need to multiply both sides by x plus 2. You're going to multiply both sides of this expression by this whole denominator. So when I clear denominators, I'll be left with x squared plus 2x minus 1 on the left-hand side. I'm going to do it all at once. It's not hard. Think about what happens when you multiply just this term by this whole denominator. X times a over x, the x's will cancel. And then you'll be left with these two. So I'll have a times 2x minus 1 times x plus 2. If I multiply just this term by this whole denominator, the 2x minus 1's will cancel, and I'll be left with x times x plus 2. So this is going to be bx times x plus 2. And if I multiply just this term by that whole denominator, the x plus 2's will cancel, and I'll be left with cx times 2x minus 1. Now this looks like an equality between two polynomials. So if I can collect all the terms together, all the like terms, like all the x's, x squareds, x cubes, whatever on the right-hand side, then I can do the thing up here, where we just set the coefficients equal. Is everybody with me so far? Alright, again, I'm going to do the algebra quickly. You could take a lot of time here and FOIL each of those things out and like go slow about it, but if you want to be quick about this stuff, here's what you do. You ask, from this first chunk, what is the contribution to the x squared coefficient? What x squareds will I get out of this? So if I were to multiply all this shit out, I would have 2x times x as the highest order term. So that's a 2x squared, and that's going to have an a attached to it. So I can rewrite this as x squared plus 2x minus 1 equals 2a. That's the contribution to the x squared coefficient from the first term. What about this guy? If I multiplied all this out, that would be bx squared plus 2bx. So there's going to be a plus b coming to the coefficient of x squared here. What I'm doing right down here is I'm starting to write down the coefficient of x squared. From this term, if I multiplied it out, I'd have 2cx squared. So that's the coefficient of x squared on the left. Sorry, on the right. If we were to multiply all this out, I would have a 2ax squared from the first, a bx squared from the second, and a 2cx squared from the third. I've combined all of those like terms and written that nicely here. Now we do the same thing for the x's, for the constants. What x's am I going to get out of this? Well, 2 times 2x, that's 4x, minus 1x, 4x minus 1x, oh, that's 3x, right? So I'm going to have a 3ax, which means the contribution to the x coefficient from that piece is 3a. From this term, I would have a 2bx, so it's going to be plus 2b. And from this term, I would have a minus cx, so it's going to be a minus c times x. Alright, now I've got the first two terms, I just need the constants. When we multiply this piece out, the constant term would be negative 2, so it's going to be a minus 2a. No constants here, right? Every term is going to have an x in it, and no constants here. Every term is going to have an x in it. So that's all that work done in a single line without actually foiling anything. Slick, right? This is a really magical equation. This is the equation that is similar to this one. Because I've got one polynomial equal to another polynomial. Now the coefficients on the right are not as nice as just a, b, and c. They're more complicated. But the rule applies, the same principle. The coefficient of x squared on the left is 1. The coefficient of x squared on the right is 2a plus b plus 2c. So 2a plus b plus 2c must be equal to 1. That's coming from the 1x squared over here being equal to this. (3a plus 2b minus c) has to be equal to the coefficient of x on the left, which is 2. Let me see, do I have other colors? Where did my other colors go? This 2 has to be equal to this. That means 3a plus 2b minus c has to be equal to 2. And then finally, the constant terms have to match. Negative 2a has to be equal to negative 1. Negative 1. Alright, this is a system of linear equations that can be solved for the coefficients a, b, and c. Thankfully, the system is not too bad, and I will in fact show you an even faster way to get most of these coefficients out. But it's important that at first you at least understand how the fucking thing works, what on earth it is that we're doing. So questions up to here. This is the step most people struggle with, so please pay attention, look at your notes, make sure you're comfy. If you've got questions, ask them. Now is the best time. Okay. From the bottom equation, since negative 2a is equal to negative 1, divide both sides by negative 2, you get a has to be 1/2. What else can I do here? So I can plug 1/2 in for a in both of these expressions, but then I'm still left with two equations involving b and c. How do I solve this linear system? Who can help me? We're all going to die unless we solve this linear system. How do we solve it? We're not all going to die, but...
Plug in A.
We can plug in the a, sure. So there I'll have 2a, that's 2 times 1/2, that's 1, plus b, plus 2c equals 1. Here I'll have 3a, that's 3/2, plus 2b minus c equals 2. And that last equation, he's no longer useful. I've already gotten everything I can out of him. I can subtract this 1, subtract this 3/2, but I still got work to do. So that's going to give me b plus 2c equals 1 minus 1 is 0, and 2b minus c is equal to 2 minus 3 halves, which is 1 half. Okay, now I've got a 2 by 2 system. How do I solve this 2 by 2?
You can multiply the second function by 2 and then add them up.
Very good. Let's do elimination. You could substitute, but that's nasty. So better to eliminate, and the first step towards eliminating here would be to multiply through this guy by 2, because I've got a plus 2c here, that'll give me a minus 2c there. So row 1 doesn't change. b plus 2c equals 0. Row 2 becomes 4b minus 2c equals 1. And now I can add those equations. So if I add rows 1 and 2, I get 5b plus 0c equals 1. In other words, 5b equals 1, which means b is 1/5. Okay, I've got a and b. How do I get c?
Plug back in b.
Plug this b in wherever. Let's plug it into the first one. Hence, 1/5 plus 2c equals 0, which means 2c is negative 1/5, which means c is negative 1/10. Alright, now I've got a, b, and c. So I go back to my PFD setup. And I say, okay, that's equal to a over x. Where is it here? Can I get this in there? Yeah. So, my original function is a over x plus b over 2x minus 1 plus c over x plus 2. A over x is 1/2 over x. B over 2x minus 1 is 1/5 over 2x minus 1. And c over x, oh god damn it, c over x plus 2, I fucked up. X plus 2, let's call that a parentheses, is negative 1/10 over x plus 2. Okay, you have now completed the partial fraction decomposition for this function. Notice I haven't done any calculus yet. You see any derivatives or integrals here? None, right? Nothing. It's all algebra. Every single step so far. Factor, set up the partial fractions, clear out the denominators, equate the coefficients, solve the linear system. Every single step has just been algebra. So as you run through your partial fraction problems, remember, stop writing the integrals. Don't write the integrals as you set up your partial fractions or any of that. You step away from the integral, put the calculus down, do the algebra, then come back to the calculus. So the integral of x squared plus 2x minus 1 over x times 2x minus 1 times x plus 2 dx is equal to, I have the integral of this thing, which I can split up now. I'll write it out just this once. 1/2 over x plus 1/5 over 2x minus 1. Alright, this is minus 1/10 over x plus 2. And all of this dx. Now we split up, pop out the constants from each, and see how to handle each of the resulting integrals. So this is equal to 1/2 integral 1 over x dx plus 1/5 integral 1 over 2x minus 1 dx minus 1/10 integral 1 over x plus 2 dx. And none of these are hard. These two both require a tiny little u sub. In this guy, I will let u be 2x minus 1, which means du is 2 dx. Here I will let z be x plus 2, so dz is just dx. And the first guy requires no substitution at all. So it's going to be 1/2 natural log absolute value of x. Then you'll have plus. The differential here is 2 dx, so this 1/5 is going to be a 1/2 also. I'll write it as 1/5 times 1/2 integral 1 over u du. And then you've got the minus 1/10, nothing coming from the differential here, just integral 1 over z dz. So altogether we have 1/2 natural log absolute value of x. 1/5 times 1/2 is 1/10 natural log absolute value of u. Then minus 1/10 natural log absolute value of z plus a constant. And then finally we plug back in the u and the z. So this is 1/2 natural log abs x plus 1/10 natural log abs 2x minus 1 minus 1/10 natural log abs x plus 2. And we could from here and from here have seen that those are going to be natural logs. These are like those u subs I talked about in section 7.2. They're micro u subs. The differential is a constant. So if you can jump from this line to this line without missing the 1/2 factor here, right, that turned the 1/5 into a 1/10, then I invite you to do that. But please make sure you're careful. That's it, we're done. So these problems are a little bit involved, but the vast majority of the work is in the algebra. If you could get rid of one part of this whole thing, if there was one chunk here that you could make more efficient, what would you want to make more efficient? Looking at. I know what I would like to make more efficient.
Professor, could you put the last part real quick? I'll take a picture of it. You can keep going on what you were saying.
Here we go. Yeah, I'll refill my.
Thank you.
I think finding A, B, and C was the hard part there, don't you? Writing down the partial fraction setup wasn't hard. Factoring that denominator wasn't hard. The vast majority of the work is between the PFD setup and solving the integral, right? It's all this stuff. And I mean, I moved pretty quickly to go from here to here, right? It's not unlikely that you would take longer to go from here to here the first 10, 15 times you do it. And then you have to solve a linear system, which is time consuming in itself. Wouldn't it be nice if I could go quickly from this line to having A, B, and C? The answer is yes. Yes, it would be nice. And thankfully, sometimes we can. So what I'm going to do now is go back to this step and show you a quick way to recover the constants A, B, and C. And this will be the last thing that I show you guys today. This is called the heaviside or cover up method. And this is how they teach it at MIT. Unfortunately, so Oliver Heaviside was a dude, a mathematician, and he came up with this trick for quickly evaluating these things. The kind of way of thinking of it in terms of cover up is like you literally cover up one term down. I don't like that. But from this line, we can. So what should I call this? Let me call this 2 star. I called the other one star. I need to refer to it somehow. In the equation 2 star, we can send x to any number we like. Right? This equation is supposed to be an identity. It's supposed to be true for every x in the universe. So if I want to plug in some x values here, I can. No one can stop me from doing that. In particular, I can send x to some values that make these two guys disappear without making this guy disappear. And then that will let me read off the value of a. Separately from that, I can send x to a value that will make this guy and this guy disappear without making this guy disappear. That will let me read off b, and so on. So, as x goes to 0, what does that line become? I'll have 0 squared plus 2 times 0 minus 1, that's minus 1, is equal to a times 2 times 0 minus 1, which is negative 1, times 0 plus 2, which is 2. And then here I'll have b times 0 plus c times 0. Both of these terms are 0 because they both have this factor of x. So what do I get? I get negative 1 equals negative 2a. Divide both sides by negative 2. 1/2 equals a. Quick and easy. As x goes to 1/2, see, I'm choosing this number. I chose 0 because I know that this factor will kill both of these terms when I send x to 0. My next move here is to send x to 1/2 because I know this factor and this factor will both drop out if I plug in 1/2 for x. What do I get there? Well, this time it's a little more complicated. 1/4, 1/2 squared, plus 2 times 1/2 is 1, minus 1 equals a times 0 plus b times 1/2 times 1/2 plus 2. I'll just write it like that. Plus c times 0. Right? This factor makes the a piece 0. This factor makes the c piece 0. So I'm just going to get b's out of this.
I asked where you got the 1/4 from.
Yeah, I'm plugging into the left-hand side here. So 1/2 squared plus 2 times 1/2 minus 1. This is the 1/2 squared. This is 2 times 1/2, and this is the minus 1. So I'm plugging 1/2 in right here. So each one of these maneuvers I'm doing under the Heaviside method, I'm taking this equation and I'm plugging in some particular x value. So 1/4 plus 1 minus 1 is 1/4. Over here I'll have b times 1/2 times 1/2 plus 2. So 2 is 4/2. This is 5/2. So this is 5/4. Is that right? Yeah, that's right. And now, dividing both sides by 5/4, or multiplying both sides by 4/5, I'll get 1/5 equals b. lastly, as x goes to negative 2, what will we get? Negative 2 squared is 4, plus 2 times negative 2 is minus 4, minus 1 equals, any term with an x plus 2 is going to vanish, so this term is gone, this term is gone. I'll just have c times negative 2 times negative 2 times 2 is negative 4, minus 1 is negative 5. 4 minus 4 is 0, so it says negative 1 is equal to negative 10c, and dividing both sides by negative 10 we get 1/10 is equal to c. And I think for most people this is preferable to setting up and solving that linear system.
Where do you get the numbers from? Where you send x to?
They are the values of x that will make these factors 0. So the 1/2 I chose because of the 2x minus 1 factors. The 0 I chose because of the x factors here. And the negative 2 I chose because of the x plus 2 factors. So the numbers here that we're going to send x to are the numbers that will, one at a time, make each of the factors from the original expression 0. Make sense?
How many of those questions are we going to get on the exam?
Definitely more than one. Probably, less than 5, because there's lots of other stuff. Usually my exam one has at least one question where I ask you for a setup, and just the setup. So give me the PFD setup for this big fucking function. And then there's also usually at least one free response question where I ask you to use partial fractions to solve an integral, or I give you an integral that can only be solved using partial fractions. That's generally the case. Usually about 2 questions on the test related to partial fractions. But it could show up in other contexts. It could show up as a part of another problem. Maybe you do some, I don't know, you do some sort of substitution or integration by parts and you end up with something that requires a bit of PFD, or vice versa. I'll tell you this, it's very possible to do partial fractions and then need trig sub. We'll see examples like that, but not until Monday. So what I've shown you here today is everything you need to do all of the partial fractions problems that are in the homework set, which is up now. The homework set, which is up now, the setups are all very nice, right? You only have distinct linear factors. You have no repeated factors, no irreducible quadratics, and definitely no repeated irreducible quadratics. We will talk about those, but I want to get you comfy with the basics first. So you've got the basics now, and then on Monday we're going to look at some more complicated partial fractions problems. But this is where I'd like to switch over to solving homework problems. So if there's anything that you've seen in the homework over the last few days that you would like to address, or anything that you're nervous about being on the test, anything that you felt is like starting to drift in the past and that seems scary, now is a good time to take those up. So I'm going to go get a little more coffee, and I would like you guys to tell me in the chat which homework problems you'd like to look at in the remaining 15-20 minutes. Alrighty, let's see what we've got. Just one? Yeah, let's look at a nice challenging disk washer problem. So remember the basis of reasoning for both volume sections, 6.2 and 6.3, is to draw your region, draw your axis of rotation, and then draw a strip, a little differential thickness strip, either perpendicular to the axis of rotation or parallel to the axis of rotation. If you're using disks and washers, the strip goes perpendicular. If you're doing cylindrical shells, the strip goes parallel. Then you imagine rotating just the strip. That gives you the little volume dV that you need to integrate. Here's one from my exam last summer. Find the volume of the solid generated by rotating the region bounded by the curves y equals ln x from x equals 1 to x equals e about the line x equals -1. And we'll use this using disks and washers. So you begin with a sketch of your boundary curve. You got to identify your region. Here's what the natural log function looks like. This is x equals 1. This is x equals e. So the region that's bounded by that curve between 1 and e is this region. I guess I should say in the x-axis. Here's the line x equals -1. This is your axis of rotation. So I'm going to revolve this region around this line. If we're using the disk washer method, the strip needs to be drawn in here perpendicular to the axis of rotation. That means the strip is going to be drawn in side to side like that. So my little strip looks like this. And among other things, that strip tells me whether I'm integrating with respect to y or integrating with respect to x. Is this going to be done as a dy integral or as a dx integral?
Why?
Yeah, the thickness of this little strip is a little vertical thickness, is a dy. So that means I need to find the radii, the things that we're looking for. So the product of revolving just that little strip is going to be a little washer. And the volume of this little washer is going to be determined by 2 radii and its little thickness. Okay. So here's my washer that I would get from rotating just this little strip around this axis. The thickness is dy, and it has a little radius, an inner radius, which I'll call little r, and it has a big radius, an outer radius, which I'll call big R. dV, the volume of this little washer, is pi times the outer radius squared minus the inner radius squared times dy. So I need to know what is big R and what is little r, and I need them as functions of y. On the graph, I can label some distances, big R and little r. Right, so big R is always the distance from the far end of the strip to the axis of rotation, and little r is always the distance from the near end of the strip to the axis of rotation. Let's do big R first. What is big R?
-1 plus e.
Almost, almost. So we want to take the larger x value and subtract from it the smaller x value. So you're right, it involves e and -1. That would be this minus this. E minus -1 or e plus 1. Little r is a bit trickier. I want to take the x value here minus the x value here. I know this is -1. What's the x value over here? So this point on the curve y equals ln x can be thought of as x comma natural log of x because y is equal to the ln of x along that curve, right? That's what that means. But you can rewrite this as e to the y equals x. So this curve, or this point, is the same as saying e to the y comma y. So remember, I need both of these distances as functions of y. It wouldn't be wrong to say that this distance here is x plus 1 or x minus -1. It's just not in terms of the variable I need. This is e to the y plus 1. Oh, shit. E to the y minus -1 or e to the y plus 1. The equal sign with the top one shaky and the bottom one flat stands for the word isomorphic, if you're curious. But this tells us that dv is pi times e plus 1 squared minus e to the y plus 1 squared dy. And that means that your volume v would be pi times the integral from y equals 0 up to y equals 1 of this stuff. And from here things are pretty easy. The integral there is not a challenging one. You've got a lot of constant terms. There will be two non-constant terms. They both come from the second expression here.
Can I ask, where did you get the bounds, like the y equals 0 to y equals 1?
Yeah, sure. So we have to ask, what sort of numbers do I use for bounds here? Do I use x values or y values? Because it's a dy integral, my bounds have to be y values. And then you always just go from the smallest in your region to the largest in your region. So down here at the very bottom of this region, when that strip is at the very, very bottom, that's y equals 0. And up here, when the strip is at the very, very top of this region, that's y equals 1, because the natural log of e is 1. So this point on the graph right here is e comma 1. Do we want to see the integral worked out, or are we happy up to here?
Can you solve it, please?
Actually, I think I may not have time to. I think we are right at time here, but I can walk you through the first few steps. So this is pi integral 0 to 1, e plus 1 squared. I'll go ahead and FOIL it. It's e squared plus 2e plus 1. And then we'll have minus this thing. So it's going to be minus e to the 2y minus 2e to the y minus 1 dy. So foiling both and distributing this minus. Again, most of the terms are constant. The ones cancel, so you have e squared plus 2e minus e to the 2y minus 2e to the y dy. And then the constant terms, this is just going to be e squared plus 2e times y minus antiderivative of e to the 2y is 1/2 e to the 2y, that's a little micro u sub, minus antiderivative 2e to the y is just 2e to the y, and you would evaluate that from 0 to 1. Alright, I do think I have to stop here because I have another class that starts in a little bit. But this is a classic disk washer problem. Some variation on it shows up usually on my first test. It's got all the challenging things, right? It's got an axis of rotation, which is not the same as the x or the y axis. You've got a curve that's given to you as a function of x. You need to convert it to a function of y. And you need to think about carefully the variable you're going to integrate with respect to. Another fun exercise is to find the same volume using the cylindrical shells method. That would end up being a dx integral. The integral there would require integration by parts. It's a little tougher, but the setup is easier. So I encourage you to run back through both of these. Try this same problem on your own, and then try doing it with cylindrical shells. Alrighty, I gotta end the meeting here. I hope you guys have a lovely rest of your day. If you want to talk about anything else, I do have office hours this afternoon. Oh wait, actually, let me check my meeting schedule. I might have to cancel office hours this afternoon, so I think I have a department meeting. If that's the case, I'll host an extra office hour sometime soon. It's today, 17th. Yeah, so I do have a department meeting today. It's not a big thing, but so my is that at 2? Yeah, that's at 2. Alright, I'll let you know. I'll post an announcement. I may have to cancel office hours this afternoon, or at least move them to a later time. But if that happens, there will be an announcement on Canvas. And yeah, that's it from me, guys. I hope you have a lovely rest of your day, and I'll see you next time.
Thank you, Professor.
Thank you.